Hey, welcome back, physics. And as you can see, we are still in my living room, and I'm wearing the same shirt I was wearing last week, which is either really bad laundry or I recorded it on the same day. You be the judge. But we are here again looking at Chapter 14, Sections B and C. And that is going to be entirely review for you. You're not going to learn almost anything new. You had this in physical science. You had this in chemistry. You now get it again in physics. So third time's the charm. If you ever weren't sure about some of these things, now's the day to be solidified and confident, okay? I almost actually skipped these last two sections, just like I skipped parts of 13, but I figured it was important enough for going forward that you needed to have the review. So this should be an aha, I remember that lecture, not a, that's interesting, I don't know that lecture, alrighty? So we're going to go appropriately fast through these things. Alrighty. First of all, there's a new vocabulary word that you might not have heard before, thermometric properties. Thermometric properties are characteristics of a substance which change because of its temperature. And its temperature, remember you already know this, is its average internal kinetic energy. The amount of motion inside something taken as an average across the whole object is its temperature. So, thermometric properties are things that change when the substance has more or less kinetic energy. The example from the last section of the chapter was volume and length, which are two of several thermometric properties. Among them would also be electrical resistance, which we'll get to later, and density and viscosity, and there's lots of thermometric properties, okay? This chapter focuses in mostly on expansion. But there's others that belong in that group. We use bimetallic strips in thermostats, and your textbook makes a big deal about those, and they are cool. You have two different metals bound together or fused together into a long strip, and then when the temperature changes, they expand or contract at different amounts because they're different metals, and so the strip will curl and twist based on the amount of temperature thermal expansion going on there. And we use those for many things, including thermostats. And then the expansion of liquids in a thermometer. That's how thermometers work. It's a little evacuated glass tube with a small amount of red alcohol or a small amount of mercury in it. And that liquid is free to expand or contract based on its relationship to the temperature. And that's how we read the thermometer. So thermometric properties, things that change when they get hotter or colder. Okay. The history of taking a temperature. Here we go. Here's something you never thought you'd learn in school. Galileo was the first to try to take a temperature of something. He built two examples of how to measure temperature. Neither of them were very useful, and nobody used them after he died. So thank you, Galileo, for trying. We appreciate it. Others did better. It was replaced by the work of principally three different people. Fahrenheit's work. He came up with some of the first thermometers that we would recognize as a thermometer. And he came up with a temperature scale that America is the only one who uses. Go Marca. And he set his gauge with 0 degrees being the coldest he could make something with ice, salt, and water. And so basically the freezing point of salt water is 0 degrees Fahrenheit. And then he initially tried to set the scale at 100 degrees being the internal temperature of a person. And then later he reset his scale, and our body temperature wound up being 98.6, not something that is easy to remember as a benchmark. But he used 32 degrees as the benchmark for the freezing point of water, and 212 degrees Fahrenheit for the boiling point of water, set a scale on those three things. Okay? Nobody else but America uses this. Why do we still use this? I don't know. Write your congressman. Okay. Then this is Galileo's two attempts at a thermometer. So here we have up here an evacuated airspace. This is a vacuum, and this is a liquid, and it doesn't really matter what the liquid is. As the airspace in here gets hotter or colder, the few molecules that are up here cause this volume of airspace to expand or contract with pushes or pulls water up the tube. And so the height of the tube, the height of the water column helps the person understand relatively the temperature, okay? Problem is that it's also impacted by barometric pressure, atmospheric pressure. So when the water column goes down, it might be because the temperature is increasing, or it might be because the pressure just dropped outside because a rainstorm's coming in. This is Galileo's other experiment with temperature. He has glass with various liquids of known densities in it, and he hangs weights off of these various ones to make the net density of the object be exactly what he wants it to be, and then he allows the liquid in the tube, the clear part, to be whatever temperature the outside is, and that changes the density of that clear liquid, which makes the various spheres rise or fall based on their relative density. So if you can read one of these things, you would look and say, oh, red, black, green are up, but yellow and blue are down, and that would tell you that it is some kind of degree temperature or relative temperature, okay? Again, kind of a cumbersome way to do it, and you don't necessarily know exactly at what point yellow starts to float or green starts to sink, so it's a hard tool to use. But these were Galileo's 2 attempts, okay? And then Fahrenheit replaced these, and then Fahrenheit was replaced everywhere except here by Celsius's work. So Celsius was a European, and he came along with, he was doing his work during the time when the metric system was taking effect, and people liked everything being divisible by 10 because why not? It's easy. And so he didn't set his anchors at 32 and 212, and he just said, hey, look, water freezes when it's this cold. Let's call it 0. Water boils when it's this hot. Let's call it 100. Oh, that's a lot easier. It's a lot easier to work with 0 and 100 than 32 and 212. So scientists adopted it. It became the official metric scale, and the rest of the world took off with it too. But it still left a couple of questions unanswered. Everybody knew that 0 Celsius was not as cold as it could be. You could actually quite easily have negative something degrees Celsius weather, like all the time. So it got colder than 0 Celsius. How much colder could things get? And they didn't have an absolute sense of thermal energy and an absolute sense of scale. And so this problem was addressed by a very, very famous British physicist who happens to also be a titled lord, and his name was Lord Kelvin. Lord Kelvin worked with Charles, the same Charles of Charles' Law, which we'll get to in just a moment, to come up with the absolute 0 scale, or the absolute temperature scale. After he died, it was changed from the absolute temperature scale to Kelvins in honor of Lord Kelvin, who worked on this problem, okay? 0 Kelvin is described as absolute 0. It's the coldest possible temperature at which all molecular motion stops. And you would think, well, can't you get colder than absolute 0? Nope, because nothing, you can't take heat energy away from something that has no heat energy, okay? 0 Kelvin is also, in the Celsius scale, is also negative 273.15 Celsius. So that's the equation there. They have the same amount of thermal energy in the units of Kelvin and in degrees Celsius, just a different calibration. So the Celsius scale has the same width between numbers as the Kelvin scale. It's just that they have a different 0, okay? And you never say degrees Kelvin. For some reason, I don't know why, it seems silly to me. You just say kelvins. So 13 kelvins, not 13 degrees Kelvin, okay? Keep that straight. All right. Conversion factors. Don't use the ones in your book. They're silly and complicated, and I don't know why they gave you them. These are much easier. Pause the video, write these down, okay? Temperatures Fahrenheit to temperature Celsius is just Celsius to Fahrenheit is degrees Celsius times 1.8 plus 32. Going the other way around, Fahrenheit minus 32 divided by 1.8. That's a lot easier than what it told you in your book. And then plus or minus 273.15 will convert between kelvins and Celsius, okay? How do you go from Fahrenheit to Kelvin? You go through Celsius, and then you make the other conversion, all right? So make sure you use those. I don't know why the book gave you the ones that did. Weird stuff, okay? Gas laws, 100% review. We went through this in physical science. You went through it in chemistry. You spent a long time on this in chemistry, and now you get it again. So real quickly, Charles' law relates volume to temperature. Volume 1, temperature 1 equals volume 2, temperature 2. So if you change the volume of the gas and you leave everything else the same, its temperature will change. If you change the temperature of gas, leave everything else the same, its volume will change. That's Charles' law. Boyle's law relates pressure and volume, okay? So as pressure goes up, volume goes down if temperature is held constant. Then there's Gay-Lussac's law, who related pressure and temperature. Pressure and temperature Pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. And then there's the combined gas law that puts all three of these laws into one expression. Pressure times volume divided by temperature is a constant. So you can mess with any of those and use the other side of the equation to figure out what happened. All right, you did a ton of that in chemistry. Please tell me you remember how to use that. And then, of course, there's the ideal gas law, the Thermometric gas law. And we did a bunch of stuff with this too, and you will get it again here. So pressure times volume equals the number of moles of gas times the gas constant times the temperature. What does R stand for? It depends on what your units of measurement are. There's a table in your book that gives you the different values for R. I will not make you memorize it. I will always give you that table, or it'll be an open book thing where you can look it up. So don't stress about what R is. You can always look it up. Okay? That is all she wrote, folks. 10 minutes and 55 seconds of review from chemistry once again for you this week. God bless you. Have a wonderful evening. If you have any questions, post them in the comments field below. I'll see you tomorrow. Peace be with you.